Okay. Evaluate division. You are given an array of valuable pairs equations and an array of real numbers values, where equations is AI BI and values represents the equation A divided by B. Each A or B is a string that represents a single variable. You are also given some queries where queries J, and I guess it's J because it doesn't want to, so, because these I's line up, so it doesn't want these to line up. It represents the Jth query where you must find the answer for C. Okay, so it's like we're given a problem set. Okay, that's a good one. Let's do it. All right, so right off the bat, um, basically, this is trying to find transitive values. Not transitive, but like, what's the word? It's close to transitive. So if you have so in the example, we have A divided by B and B divided by C, and we want A divided by C. If a single answer cannot be determined, return -1. So I don't think it's actually a matter of finding out all the values, otherwise that would be the challenge itself. Also, the values themselves could be at any sort of scale. Like you could have, like 5 and 2 could be 50 and 20 just as easily, and the result would be the same thing. So it's not asking about the thing. Also, the outputs here are using an awful lot of they're floats, so we're not doing like floor division or anything. Okay. The input is always valid. You may assume, so we don't have to. So there's no contradiction. Thank goodness. Okay, so what are the topics of this one? So let's see. What I'm thinking is that we turn the equations into a, turn equations into an adjacency matrix, or actually, sorry, turn them into into a directional graph. With the direction being that if you have A, C, then you want to find the path from A to C, because the answer will be all the values in between divided by one another. Okay. So we turn them into a directional graph. Then, I mean, we should probably do like Dijkstra's no, wait, it's not Dijkstra's algorithm because they're not weighted. Well, the problem says shortest path, which would make me think breadth first search. I think it would be so for a shortest path, we'd want breadth first search. Okay, so we're trying to find the path from A to C in this. So we have this adjacency matrix this graph, and that graph will be represented by a map. Where the key is the value is the numerator, and the value is all denominators. Okay. So then we would say so for every query, we're trying to find the shortest path from A to C. And the shortest path, the best option would be a breadth first search, because that finds the solution as soon as it sees it, rather than, it could potentially go really deep into the graph and find nothing. So what do we want to make sure? To ensure no cycles in search, so we keep track of visited numerators. Meaning that if we look at a denominator and it's already a numerator that we visited, well, yeah, if we see like, okay, we have A divides B, and then we're looking at B and we're like, okay, well, should we look at if A is a denominator? Well, we're trying to find C, and if we go to A, then we'll just get stuck in a cycle of A, B, A, B, A, B. So we could, to just keep track of that, do we want just a set of visited numerators? I think that's it. Okay. Yeah. Awesome. So let's see. So what's the steps here? First, assemble the graph. Second, and then assemble the graph. And second, for every query. Oh, wait, and the entire time also we need to keep track of the path. We also need to calculate path to that point. So to do that, to do that, let's see. So this is good, but we need to calculate the path to that point. So we need to somehow, during our search, say okay, here's my thought. Calculate the path to that point. What to do that, we adjust the okay, I got it. Adjust the graph to retain the vowels of that calculation. E.g., A points to B, val is 6. No, sorry, val is 2, because AB correlates to 2. And so we'd have A key equals A, val equals a tuple B2. I think that's it. Okay, let's do that. Assemble the graph. Okay. For I, we'll use I so that we can access both the equations and the queries. I'm going to turn on some music too. For I in range, we just want like n, I don't know. We'll say n equals length of equations. Range n. We're going to say, oh, let's use a default dictionary also. Graph equals, we'll say n to d graph, numerator to denominator graph. N to d graph equals default dict. And it's by default, it's a list. Okay, so later on, when we recursively go through that, or not recursively even, well, yeah, recursively, we want to access the values in that graph, and we don't want to have to check to make sure it even exists, so we can just say default dict list. Okay, so first we assemble the graph. Okay, so we're going to say for I in range n, we're going to say n to d graph, or we'll say numerator equals equations denom equals numerator denominator equals equations I, how we can say equation E equals E equals equations I, and then numerator denominator equals E0 E1. Cool. Now we're going to say n to d graph numer, and we can just freely append it. We don't have to check if it exists because we have the default dictionary. We can say append. We're going to append a tuple, where that tuple is going to be, oh, this is so good, values I, and yeah, this is really working, denominator. So now we have a dictionary where each value points towards all the values that divide it and the result of that division. And then, oh wait, I have another thought to save time, because I think it's being extra cute. It's not just doing this for, the point of the problem, I think, is not just that you're doing, this division, But also, because, it could just run a billion test cases. So why would you have to do multiple queries? And I think the reason why is because we can add the query results to the equation. So if we have like A to Y and we process that whole thing and then we get A to Z, we don't need to end Y. We have Y divided by Z. We can just we can hold on to those values. So basically we're going to remember this result, and we also are going to need to update it accordingly. We can just update the graph. We don't even need to update the equations values, because now we're just working with the graph. Oh, this is so good. We're doing so good. Okay, so we'll just say for query in queries. If we need to do an index loop, we'll change it later. Okay. We also need to worry about what happens if we don't find the path. So let's see. Just want to look at all the constraints. Okay. So for query in queries, this is going to be the tricky part, is the actual recursion. Do we want to just have a recursive helper function? Do we need one? Do we need one? How is this going to work? Breadth first search. This is feeling to me like a breadth first search, because we want to look for the shortest path. Because that's just an easier calculation. For query in queries, actually, okay, one thought is, do we actually want this to be a default dictionary? Because it's possible that, because one of the conditions that it mentioned was that you're given variables that don't exist. But if that's the case, then I think you just won't find any things that it pairs with, so you're not worried about that. Because, like, let's say we get a numerator that doesn't exist, it's going to say, okay, well, look at all the available denominators, and it's going to find nothing. But then again, we could go through that logic and find that, well, maybe we just need, like, because we also need to worry about, I think that the only time, so I think that they're trying to give you a hint with these two. We have AA and we have XX. You could get A by saying, You could get AA by, I think that maybe we just had to not do a default dictionary. I think that's what it is. Not doing default dictionary as a variable not being present. Oh wait, but that's not necessarily present. Present is important knowledge. You understand? So basically the only reason why we treat A different than X is because X is something that we haven't seen yet as a thing. Oh, this is annoying. Because you could have an equation that would be AA. There's nothing that's stopping that. Which would mean that A would be present, but X isn't. So A, you would need to calculate I think we just need to make this be this. Or we just get even more complicated and we say have a scene variable set. Okay, that's a better way of doing it in my opinion, because then we don't have to worry about all the edge cases. We can just say if we haven't seen either of the variables, then we return -1. Okay, so we're going to say, and we'll say scene variables equals set, and we'll say scene variables add numerator and scene variables add denominator. This is going to be useful. So it's a set because that way we don't have to worry about adding it twice and unnecessarily using up memory. So we're going to say if, we'll say we're going to say if numer in scene variables I guess we should probably do I because we want the output. So we'll have answer equals -1.0 for blank in range length of queries. And then we can say for j in queries. Oh, that's good. We could also just do times length of queries. Okay, so now when we don't get an answer, we don't need to set it to -1. It's just its default value is -1, and otherwise we update it. At least I think so. Or denom not in scene variables to get finicky with these. I'll say this. If either of those are true, then you return, well, then you just continue. So if we're given variables we haven't seen, that answer stays at negative 1.0. Otherwise, we now start our breadth first search. My question is, do we want to make this be recursive? I don't think it needs to be, but what's the answer here? Okay, breadth first search. So, add to the queue all the denoms of the first numerator. Okay. Add to the queue all of the denoms of the first numerator. Add the first numerator to a seen numerator set. Okay, and then this will help us make sure that we're not looking at the same numerator twice, or that we get stuck in a loop of numerator denominator of a, b, a, b, a, b, so on. Okay, add to the queue all the denoms of the first numerator. We could say if numerator equals denom. I think this is just an edge case. I think we are going to consider that. Edge case a over a. Then we say ants j equals 1. 1.0, I guess. Okay. Otherwise, we start the thing. We'll say q equals q equals numer. And we'll say seen numerators equals a set of numer. So this keeps track of all the numerators that we've already looked at. Actually, we'll say visited numerators. Okay, now we'll say while q. So while we have numerators left to look at, oh wait, okay, I've got an idea. The q equals okay, wait, okay, I'm gonna write it and then I'm gonna see if it works in my head. Okay, so we'll say new let's say visited numerators. Okay, wait, while q, we'll say active numerator equals q dot pop 0. Visited numerators add active numerator. All right, and then we're going to say for denom in this graph, n to d graph, active numerator, we're going to say q oh, this is so it q add or q append active numerator divided by d. We can also say, oh, no, wait, that's not it. It's almost it. That's almost it. I think I'm losing track of the thing I did before, where it was like tuples of the denominator and the value. So a divided by b is 2, and b divided by c is 3. And one of the queries is b divided by a. Oh, so I didn't think about that. It can be bidirectional. It would just have to be the inverse. The inverse value. 1 divided by val. So we're going to do the same thing, n to d graph. Append denom, append numer, and then 1 divided by values. Oh, that's cute, because that's the same thing. Right? Yeah, because we have a divided by b is 2. That means that b divided by a must be, is the that to the negative 1, which would be 1 divided by values. This is exhausting. Okay. Now, what we need to do, we've got the active numerator. So a divided by b is 2. And then b divided by 3 is 6. So they multiply. I think we just multiply the values, right? I guess. I mean, that's what we're given. Okay, so the q is actually going to start with So here's my idea. The Q is going to actually be numerator and 1. So we start with it at 1. For all the denominators that the numerator attaches to, active, we're going to say if D not in visited numerators, we're gonna basically calculate it out by saying Q dot append oh, this is tough. This is tough, but I think I'm almost there. Q dot append if D is not in visited numerators. So if we haven't already seen that as a numerator, then we're going to calculate it out to be the new numerator. Append. Okay, here we go. Okay, Q dot append okay. Q dot append D D0 and active numerator one times D1. Whew. Okay, I think that's it. Basically, we're saying, okay, then we have this queue of numerators to go through. So like A doesn't quite reach C, but it reaches B. So then now we do B, but we need to keep track of what the value is up to that point. So we multiply 1 as a starting value times the value of B, which will be 2. Oh, this is so it. Okay. So we also need to check to see, we'll say if D0 equals query 1, so if it's the denominator that we're looking for, then we're going to say we can just empty the queue after we... Oh, this is so clever. Then we'll empty the queue after we say then the active value, the final value, ants j equals active numerator 1 times D1. And then by doing this, it ends the queue, and so it stops this breadth first search. And by saying break, it stops this. So as soon as we find the answer, we stop it all. We should also calculate the solution. So we can also have a cache of previous solutions. So we can say basically just update this. We don't need to worry about we'll say this. We can say answer equals active numerator ans j equals answer. We don't need this. Actually, we can just say query 0 and query 1. And if this works, I'll be very happy. Honestly, I'm feeling pretty good. I'm sure that there's like a syntax error or something that I mixed up along the way. But this actually could be it. And then just return ants. If this works, I'm gonna go nuts. That's insane. Let's see this. So okay, wait. Okay, I think that's everything. Oh, we need to return ants after the loop. For j in range length of queries. We could say qn equals length of queries. I will go nuts if this works. That's right, we need to say query equals queries j. Oh, I hate you so much. Oh, that was almost it. Oh. That was so close. Well, may I say, I am shocked that it worked a little bit. Not shocked, but like it's really cool that it worked for those cases. I guess there's an edge case I didn't consider. Okay, so I was saying, so we have A, B, B, C, and we get, yep, 6, 5, -1. So we haven't seen E, so we can't calculate that. A would just, it's an edge case of 1, and we haven't seen X or X, so yeah. But actually, since we know, really, it's like a bidirectional graph, because for every AB, we can figure out BA easily. Oh my gosh, so what did it not work for? Do I have to debug this? I'm just gonna, I don't care. I'll do breakpoints for everything. I know I could just step at that point, but you know. Okay. Let's debug. So what did it not work for? So x1 to x5 should be 360. And we got it. What did it not work for? x5 to x2. So x5 to x2 should be 1 over 6 times 1 over 5 times 1 over 4. But instead we got the other way around. What's 1 divided by 120? Okay, so it's not like an edge case. It's actually just wrong behavior. Okay. Okay. So the first answer we get right. So we'll just step through until we get the answer. Oh, wait, did we forget to delete this? No, that's right. So x1 is looking for x5. So we say, okay, so 4D and 2. So we pop 2 because x1 only is attached to x2. So now the active numerator is x2 with a value of 3, which makes sense. I'm going to say, okay, so it wasn't the answer we're looking, it wasn't the denominator we're looking for, but it is in the visited numerators. So now, is x1 attached to any more? None. Really? What's d at this point? x3 is 4. So now we're going to append x3 with a value of 12. That's crazy that I was able to, okay. So now we've seen x1, x2, and x3. So 4D, so now we're going to do the same thing. We're going to say, okay, x3 is attached to x4, so now it'll be x4 with a value of 60. Okay. Let's see, so x4 is attached to x3. Oh, that's why it's going through it twice. It's because it's going through the backwards one first. So now we say x4 we should be looking at, yep, x5. So the answer is 360. Numerator, denominator are the original queries, so that we can update the equation matrix. Answer J equals the answer, and we set the Q to be 0, and we break. And then that will stop the Q. So now we move back to the next query. So this is where it got funky. Query equals queries J. Okay, so now we have the numerator. So none of the edge cases come up, but the numerator, so we have x5 and x2. And let's see, so we just added that x5 to x1 is 360. Did we flip it? Did we like accidentally flip it? No. Oh, wait, is that it? Did we just not flip it? Oh, wait, we never inverted it. So now we're looking for x5 to x2. That's totally it, is we never actually inverted it. Come on, let's see if this works. Oh. That was tough work, but we pushed through. So not good on memory, but pretty good on runtime, all things considered. I'm okay with that, considering I'm surprised I was able to get the answer at all. I think maybe it would be better on memory if I just didn't do it bidirectionally. But this makes sense in my head. To reiterate, what I am saying is we are... Okay, let's see if I remember the code that I just wrote. It's that complicated. I was starting to debug, but I had it right the whole time. I just forgot one little thing. So we make a graph. That graph contains all of the numerator-denominator relationships. So for every n, all of the numbers that divide it and the results of that division. And we do it the other way around, because if we have a b equals 2, then we know that b a equals half. And by doing we just flip those and we just invert the result. Easy peasy. That's useful because now what we can do is we can try to find the shortest path between 2 points. So we go through all the answers, and I like that little detail. It's not just for one query; it's for a list of queries, because that way you can build up the answers over time. And we say, because we have the number of queries and we have the answers for all the queries, we start them at -1, and we just don't update it if we don't find a solution. Which is good, because once we while Q, if that gets through and it never finds the answer, then it just won't update it. So first thing, we handle the edge cases of if we've seen either of the variables, which we handled by having a set which holds on to the seen variables. I like that because that way we can use a default dictionary and we don't have to handle the case of what if we haven't seen these. We don't have to handle the case of initializing the values. They're just all initialized as an empty list. Probably not the best for space, but makes it way simpler in my head. So query equals queries j. Numerator, denominator is, so we're looking for the relationship between numerator and denominator. We check if we've seen both of these variables, and we check if it's they're equal, in which case we don't even have to try to solve it. In fact, we probably shouldn't. And yeah, well, because we know what it is. It's always going to be 1. We don't need to be told that. And there's no other case in which you'd want, because the equations don't account for that, so we wouldn't be able to find it otherwise. So now we have a Q, and this Q holds on to all of the results of dividing the numerator by all of the denominators in the listed equations, and a tuple where the second value is the active value of this division. So now we have visited numerators, and this will help us ensure that we don't look at the same numerator twice, because otherwise you could get a divided by b, and then you could go, okay, well, b gets divided by a, and a gets divided by b, and so on. This helps us stop that. So we pop off the active numerator. Everybody has to wait their turn. Maybe we could just do a stack, honestly, but whatever. And we say, okay, so add this. We've now looked at this as a numerator. So if we see it again, don't try it as a denominator, because then we'll just get stuck in a loop. We iterate through all of the denominators that this numerator gets divided by. And we say, okay, well, if this is the denominator that we're looking for, then the answer is just the results of the current value that we're at times the results of this denominator for this numerator. What's nice is that we might get no, yeah, that's right. All right. Then if we get the answer, then we update the adjacency matrix accordingly, or the graph accordingly, because for future queries, if we have one that if it's a to y, and we have a to b, well, a divided by b, b divided by c, and so on, and we calculate a to y. If the next puzzle is a to z, we don't want to recalculate the whole thing when we could just say a to y and then y divided by z, and so on. Yeah. So then we update that answer array, and to stop the recursion, or not recursion actually, but just the breadth first search, we just empty the queue. We say we don't need to look at it anymore. We found our answer. If D was in numerators, well, is not in, otherwise D is not the answer we're looking for.
and we say if D is in visit, it was not in visit enumerators, meaning that we haven't already tried it as a visit enumerator, then we append to the queue that denominator as the new numerator, and then we update that active value. So A divided by B is 2. So now we have B and with an active value 2. So now we're looking for B divided by C, and we get B divided by C, and then so we multiply 2 times 3, and we get 6, and that's our answer. And then if we don't find the answer, we just never update the value. Oh my goodness. Thank you for bearing with me if you watched that. I hope that this helped you at all as I understood it. Thank you a bunch. Have a good one.